I uploaded midterm answer key this afternoon, and you can check the answers in blue. Okay. So this question was about concept of stationarity, and this one is to write this output in this representation. And something about information criterion. And something about dummy variable. And then forecast, two-step ahead forecast for AR1 process is, of course, very simple. And bootstrapping is to draw some values from the pool of fitted residuals. Okay. Augmented Dickey-Filler test is to test whether this is 0. Okay. And under the null hypothesis, this test statistic, which is t statistic, has non-standard distribution, something like this. You can illustrate it. Of course, t distribution, usual t distribution, have center 0, and it has a mass to the right of this distribution. In the volatility model, writing this output in this form. Okay. Mean equation and the variance equation. And sum of these two coefficients is less than 1, so it's stationary. And the baseline volatility is computed as the ratio of this constant to 1 minus the sum of these two coefficients. Okay? Monthly standard deviation is annualized by multiplying square root 12. Okay? Then how to write this in Garch representation? Of course, the answer is right there, right? So mean equation is the same as before with different parameters, estimate. And if we write this term in expression, it has something like this one. And this was the key. This negative significant value is indicative of leverage effect, asymmetric effect, okay? Which is this one. Right? EWMA is computed in this way. So how to initialize this computation when you have a stock price, not a stock return. Okay? So first we have to calculate stock return as a ratio, log of ratio, this ratio. And to initialize it, you just calculate the product and take square root. So that's this is volatility, right? Not the variance. So this is volatility. And then calculate this side and take square root, and that's C4. Okay. So something similar to this one is what I expected from this question. Okay, so you can download this file from the web. Okay, this week we'll study time series model. Unlike the the previous models, it has nonlinear feature. Of course, we have seen two types of nonlinear model already. One is Garch class model, and we'll get to that shortly. And second, regime switching model. That's also another nonlinear model. So here, when you're given this type of data, let's say 1,000 observations, I simulated this X from this process, which is known as bilinear model. And as you can see, the term, the cross term, like this one appears. And so essentially, it is not linear in this formulation. But if you have X and actually calculate expected value, if it is IID sequence, obviously this is constant and this is the uncorrelated, and so the naturally expected value is 0. And if you calculate a covariance between observation at t and t plus k, it has expression like that. But if k is not 0, the case of k being 0 is the variance. And if it's not 0, then we can show that the covariance is in fact 0 or 0. So if you are given this kind of data, you can typically find 0 expected value and no correlation, autocorrelation. So you may think this is white noise. But in fact, because of the structure in this part, it is predictable because one step ahead forecast can be calculated in this way if you are given fitted residuals. Okay. So it looks like white noise, but because of this nonlinear structure, it has some portion, systematic portion, that may be predictable. So that's the one example of nonlinear time series. Another example is this. Do you see? It is expressed in terms of product, right? Product of something, right? This one, if I rewrite it in this way, and this is what we call arch-1 process. Arch-1 process. So if you calculate the mean of xt, which is 0, because this is known at t, it's a constant, and this one expected value of epsilon t is 0. So expected value is, of course, 0. The variance, because this is constant, and usually it is assumed that this one has a unit variance. So the variance of xt is sigma t squared, whereas expected value is 0. So you can do the same calculation using this formula, taking expected value, all known at t. So expected value of that is 0. So expected value is 0. The variance is, of course, this one to the power 2, raised to the power 2. Okay. So same expression. Okay. So that's so typically we had in a linear model a very simple structure, right? But we could have some structure like this one among residuals. So this is one example, and this is another example. Okay? Let's take a look at other simulated time series, assuming different processes. This one is typical autoregressive process like that one. Okay? So there is a mean, and it's going moving toward mean and deviate away from mean and come back, right? So mean reverting process, stationary process. This one is called generalized autoregressive process. It has more feature, and I'll show you how it looks like. And if you just look at this one, because it has autoregressive feature, it might show some sort of autoregressive pattern like that, right? But it is more complicated than simple autoregressive process. The bilinear model is the one we've seen already. Okay? And this is a threshold autoregressive model. Actually, there are two autoregressive processes here, depending upon the value of x. So if value of x exceeds particular threshold, or if fall below that threshold, then it follows one autoregressive process over the other. Okay, so we'll see that one also. So here is the expression known as generalized autoregressive model, where you have starting point is, let's say y is function of past observations, and in this case the functional form is very simple, right? This one, and depends on only one lagged value, like this one. But in general, this function could be something else. Right? So one way to approximate this unknown function is to use something known as Taylor series expansion. Okay. So here is a autoregressive part, and there is a cross products. So by introducing more of these terms, you can actually approximate this function. So think of this way. This particular model, if pi is positive, of course less than 1, then observation will lie here. Right? Then we might approximate or represent it in this relation. Right? So that's this model. Okay? Suppose instead observations are scattered around in this region. So there is a functional relationship, right? But this doesn't look like a straight line, right? may be curved. So how to approximate this function? Sometimes it could be more flexible than that, right? So to capture that effect, you introduce this cross product. Obviously, it is not a pleasant task to find appropriate value for P, R, and S, right? But because at time t, all those lagged values are known, so you can find those parameters by minimizing sum of squared residuals, right? So try different combinations for that, and try to calculate sum of squared residuals, and try to find in what combination you obtain the smallest sum of squared residuals. Bilinear model, I think we have a typo here. Has to be epsilon t minus I, epsilon t minus j, cross product. It's a typo. So the motivation of bilinear model is to use moving average terms, the lagged values of epsilon, basically, and the interaction autoregrams and moving average term to approximate a high order GR model. Okay. So by introducing various combination of this, maybe you could approximate this one. Right? Come to think of it, because of this feature, it could be y as long as it is lagged variable. Okay. There is no limitation about how to write this type of model in terms of cross product between lagged y and epsilon, or lagged epsilons. Right? Actually, simple linear model is very easy because it is very straightforward. But in nonlinear world, well, it is very difficult to determine those right combinations a priori. So relatively little research has been done using this type of model. Okay? Once you away from linear model, what is the difference? Well, the world is not blue anymore. If you have a linear model like this one, then least square estimate has desirable property known as blue, best linear unbiased estimator, right? But when you consider nonlinear model like this one, then that property doesn't hold anymore. Okay? And also we know that when you fit this model, you calculate coefficient of determination or adjusted R squared, right? This is meaningful in linear model. Okay. So things get different when you introduce nonlinear model. Nevertheless, there are several applications we can think of. Before that, the threshold autoregressive model I mentioned previously, TAR class model, is basically autoregressive process in this simple example. It could be general ARP process. But the condition, if the previous value is, let's say, positive. So in this case, threshold is 0. Okay. But sometimes threshold may not be known, so you may have to estimate what would be the reasonable threshold. Okay. I mentioned that this type of model can be estimated using nonlinear least square. But this threshold model, I think, has more empirical application than others. So let's talk more about this TAR class model. So suppose the variance of these two epsilons are the same. Let's say sigma squared. Okay. Then this expression with this condition can be written in this single equation. So we introduce indicator variable I of t equals to 1 if it is positive, otherwise 0. Okay? And rewrite this expression into single equation like this one. So because we assume that the variances of two error terms are the same, we have the same epsilon. So if this condition is met, first expression is simply xt equals to alpha 1 xt minus 1, and this term is 0, drop out, and epsilon t, which leads to this expression. Otherwise, xt equals to that expression, right? Then you can estimate this one quite easily. So first, introduce a dummy variable I such that it takes some value 1 if it is positive, otherwise 0. Okay, so create it from t equals to 1 through capital T. And let's say we introduce xt minus 1 plus and xt minus 1 minus variable, which is defined in this way. Okay? So if it is 1, then it has a value, otherwise no value, right? Okay, so this one. So we have xt minus 1 data, okay? We have it, right? It is either 1 or 0, right? So we multiply it, and that's your xt minus 1 plus, right? We have this, and you have this variable created, so redefine it as 1 minus that, and then multiply it. So you have another variable, right? Then we can run a regression of xt on either this or that. Right? Okay. Similarly, you might want to consider, let's say, intercept term. Okay. The threshold. Well, threshold is something like value 0, or some value this one, or some value this one. So greater than or less than, or greater than or less than, right? So in practice, you may not know where that threshold lies, right? Anders suggests that threshold value tau should lie within the band containing the middle 70% of observation. So from experiences, to have meaningful TAR class model, threshold lies somewhere in between here and there. So this is 85 percentile, this is 15 percentile, leaving this one 70% percentile. That might suggest you how to find threshold. So let's say you picked this lower bound as a threshold and fit TAR class model and compute residual sum of square for that particular threshold. And you change this one by one, fit the model, and calculate residual sum of squared. We know that the smallest residual sum of squared is desirable. So suppose you did that. Same thing. SSR, residual sum of squared, sum of squared residuals. So varying from low to high, that direction. And if you plot that sum of squared residuals, and probably that is the threshold. Tau. This is the example I borrowed from Anders. He refers to Rothman 1998 paper where he tried to model U.S. unemployment rate. Okay. Unemployment rate is these days believed to be non-stationary time series. Up until 1982, annual historical unemployment rate was regarded as a stationary time series according to Nelson and Placer's work. But later, as you have more data, and if you look at quarterly, typically unemployment rate is non-stationary. But it was a long time ago. So what he did was to first detrended log unemployment rate. We know there are many different ways of detrending non-stationary time series, right? The simplest is taking difference or taking log difference, or apply Hardwick-Prescott filter and remove trend, right? Or if you know, state space model, then you can actually compute random walk trend out of non-stationary series, and you get detrended series. So this UT is not released data. That's detrended data. So by detrending, UT is, by definition, stationary. Okay? So what I mean is, this is typical unemployment series. So if it is non-stationary, what Rothman did is to find some smooth trend, like this one, okay, and calculate deviation from that trend. Okay, that's UT. Yeah. And he estimated AR2 process for that. If you look at the sum of these two coefficients, obviously it's less than 1, but very big, right? So even if you have a detrended unemployment rate, it is still very persistent. A generalized autoregressive process where you have a cube term here, a square term here, and the product. So many different way of modeling it. So this is the final model he found. Bilinear model looks like this is the lag-dependent variable. Previous notation YT, and this particular lags. Okay. So it has autoregressive process as well as cross product. And threshold autoregressive model, he found 0.062 is the threshold. So first one, it has these two AR2 coefficient. The second, when it is below this threshold value, then this one. Suppose you are given that, well, there are many different possibility, like detrended unemployment rate following AR1, AR2, AR3, or ARP. Among those, P equals 2 is chosen as best model, right? We know that there are many possibilities here, but this particular lags and this power is selected. Okay. So you have 4 different representations. If you're actually following this type of process to find best fitting time nonlinear model, which one appears to be the best fitting model? What kind of information you may need? This was one. The leading smallest value, right? For this. But still you have to choose whether you need AR3 or AR2, right? Well, the simplest way is to calculate information criterion. So you have number of observations in your sample, right? And you can calculate sigma squared. So when you fit this model, you can calculate this one. You can always calculate sigma squared, right? And you can count number of parameters. So you can calculate information criterion, a Kaike or Schwartz. Right? So it's not like model is this big, it nests this model, this model, this model. This is nested structure, right? But the model could be like this. So in some case, if threshold is not binding, there will be one process. So this is going to be the same, right? Very similar. You see? These two numbers, when you compare that with these two, it lies approximately in between, right? In between. So this is average relationship, right? But this model may fit better, right? So sometimes you could go this way, so finding best fitting model. But if this is the situation, then you can pick which one, right? So in that case, information criterion might give you some idea which one is better. This one over that, or this one over that, something like that. Anders so in this study, data was quarterly and up to second oil shock period after World War II. He used a detrended data, right? But Anders had a different idea. So he worked with a monthly time series. And this time, he used delta UT. So just taking, because this is rate, right? Percent. So you are not calculating log difference. Just simply take difference. Okay? And he found TAR model is describing this one well, and he found threshold was something like 0.073. But this one is the original scale, so we don't know what it corresponds to, but looks like he thinks that this is a reasonable representation of U.S. unemployment rate. So just in case you have a reference, then refer to this particular page, and it will show you full expression for the estimated process. Okay. Okay, here is a different class of non-linear time series model known as smooth transition autoregressive model. Okay. This is the daily $1 exchange rate, the original one. And this is the log difference. Okay. Typically, this type of model I believe that period was sometime 1997 and 8. Okay. Before this period, usually this data is described as AR3 process. AR3 process. And then later, when you add this, then sometimes someone find AR1 and AR2, AR3. Of course, R squared value is very small. So most of the variation in exchange rates are random. And systematic part, explained by autoregressive structure, is very small. Right? Because dollar is asset, and asset prices are usually close to being efficient, and summarize all the data, so it cannot be very difficult to predict. So not surprising. But we try to model this one in slightly different form using star class model. Here, STAR, so star. Okay. It looks like this. It has similar feature like threshold autoregressive model, but the difference is this. X of t is basically AR1. Okay, AR1. Here is another AR1, right? And there is a weight function, function f, which is a function of lagged value, right? We'll explain that what is f. So if or we can rewrite this expression as 1 minus that, this one, 1 minus f an AR1 process, and then f times another AR1 process. Either way, it's the same thing. Where this f, in this case, it could be exponential function. I'll show you how it looks like below. So f of that, in this case, is defined as 1 minus exponential function. So you plug in this data, some data, and these are parameters. Then basically this function and exponential function defined in this way, this value will be bounded from 0 to 1. 0 to 1. Okay? So depending upon the value of x here, this value could be 1 or it could be some different numbers. 1, 0.9, 0.7, 0, 0.1, but bounded from 0 to 1. Okay. If this turns out to be 0 all the time, then this term drops out and usual AR1 process. If it is not 0, then coefficient will be sum of these two, sum of these two. Right? Of course, the weight. So if this is, let's say, 0.5, then mu plus 0.5 times delta is new constant. Pi 1 plus 0.5 times lambda is a new coefficient to the lagged value. So that's the what we call as exponential star or E star. Okay. There is another one known as logistic star model. L star, f is defined in this way, logistic function. So f of that is 1 plus exponential logistic function. And there is a parameter gamma and c. So this function, regardless of value y, it will be bounded from 0 and 1 again. Okay? So here is a logistic function. For different gamma. Okay. So for particular value gamma, logistic function, and this is the lagged value, right? In this case, let's say y t minus 1 in this particular illustration by Enders. So if x, the lagged value is this small, then function f has value 0. If it is about this big, then value is 1. Right? If previous value lies in between, then it's on this curve. So this value. So if you observe previous y's to this direction, if previous y's are increasing, f value increase. Right? Gamma, if gamma is bigger, then the curve have steeper curve like this one. So if value lies there, then hardly change, right? Hardly change. Value cap f hardly change, but suddenly increases, right? And then there, right? The extreme case could be this one, right? In that case, depending upon whether the value, previous value is negative or positive, function f has value 0 or 1, right? That's the extreme case. This one. Right? Then other cases like this one or that one, the transition is sort of smooth. So the name star. From moving from one autoregressive process to another, if you pick this type of a function as an f, then you are allowing smooth transition, right? Smooth transition. How's exponential function or E star model look like? For the previous value in this region, function f has value 1 and then smoothly change to 0 and similar, right? This way. Okay. So I've seen several applications usually using this logistic star model. Well, then, what would be the candidate for what would the candidate for this one? Let's say this one. So usually, what we use here as yt minus d is the lagged value. Okay, so that's the reason why I use this notation. Okay, so whatever it is, previous value, right? It could be at lag 1, it could be at lag 2, lag 3, or lag 4, right? Which lag? Which lag is triggering smooth transition? That's the question, right? So perhaps you might want to know whether xt minus 1 is a trigger value or xt minus 2. So this test, Trasberta and Anderson, well, they suggested f-test, where you have typical, let's say, autoregressive process here, and then you have cross product here. See, yd squared, yt minus d cubed. So first try, let's say, I equals to 2. So, you can put here d equals to 1. So if I equals to 1, then this is xt minus 1. Xt minus 1 squared, xt minus 1 cubed. Okay. if it is 2, xt minus 2, xt minus 2 squared, and so on. Okay? So fit that model and test this side. These coefficients are jointly significant. This one are the significant. Setting d equals to 1, 2, 3, 4, 5. Okay? So suppose you get this type of result. So first one, when you set yt minus d as xt minus 1, this is a statistic and p-value is 6.2%. Suppose this is the case. Then your null hypothesis is not rejected at 5%. Right? This one. So if this is the case, then what that means is if you set this one as xt minus 1, these are all 0. So you're left with this term only, right? So that means it's a linear model, a linear process. If some of those are not 0, so not jointly 0, that means some non-linearity going on, right? So that's the idea, basic idea. So when I tried using our $1 exchange rate expressed in return and tried this test, I found at lag 3, this statistic is significant. So I chose xt minus 3 as a threshold. So how to estimate so this is the objective function, and this is what we estimated. So I set this function f as a logistic function, and xt minus 3 as a triggering lag. Okay. So these two are parameters to be estimated, and these are parameters to be estimated. So I write this objective function in terms of this one. Okay. So you have a data, and it shows xt minus 3 as a triggering lag. Given initial parameters, you can calculate this is the data minus the whole thing. Here is this. And then you get this epsilon t. I square it and sum it and try to minimize it. Okay. So I get the estimates. Okay. Of course, some of them are significant and some of them are not, but mostly very weak. But this is just for illustration. So this is the data. So suppose these are significant numbers, and you have this x t minus 3, so you can calculate this one over time, right? Which is bounded from 0 to 1. This one. This is function f. Function f. When we see this, well, if these numbers are all significant, what it says is this gamma is very big, right? This is very big. gamma is very big, right? So it is more like this one. Right? So we don't see this graph as something like this. Instead, 0 or 1 or 0. Right? Okay, that's a stockless model. And let's take a look at the last nonlinear time series model. Here, what is called artificial neural network, particularly multi-layer perceptron model. In this representation, I write it as 1pj. Okay, so this is okay. If you look at this part, this is typical linear ARP process, right? ARP process. And similar to previous F-test, you are having term representing some potential nonlinearity, right? So basically, MLP is, again, we are dealing with some unknown function. And we've seen that from Taylor series expansion, we can set up the model as generalized autoregressive process, right? But this time, we try to set up this function slightly differently. Okay. So the way this A and N is set up is, well, there is a linear relationship summarized by this pi. Okay? P lag of them, right? Also, x1, xt minus 1 through p is there, right? P is there. And there is a function, g. Okay? Function g. So, if you plug linear combination of x, then this is going to be one value, right? Now, here 1 through j, this j, okay. What that means is, here is, let's say if j is 1, so 1, 1, 1, 1, right? If j is 2, then 0, 2, 1, 2, 2, 2, p2. Different parameters. So different weights. It's very similar to principal component, right? Different weight, then you get different number, right? How many different set of omegas? There are j. So there are j of them. Now, then what is p? This one. Well, we say, well, suppose you have different combination, linear combination with different weights, right? We have j of them, right? Is transformed into this logistic function to get value g, right? Value g of x, right? You might create, let's say, this one create value g of x, different combination will create another g of x. So suppose there are several G. Okay? And then you can use that G as an input to create another G. Right? You see? Because these are data, these are parameters, right? So this is some number, single number, right? And this one is single number. Right? You assign different weights, create different number. Suppose you did that. Okay? Then using those different combinations, you might, those different numbers, you might create new combination and put it back here, get another G, right? Then using different G's, using different weight, put it back, and another G. So you are putting, actually, you're manipulating this data or transforming data through this G function once. That's this one. If we are doing it again, and this is going to be 2, technically we call it layer or hidden layer. So let me show you how's that working using this one. Okay, here is an input, 3 numbers, right? 3 numbers. And here is a weight. We call it synaptic weights. So there are information. They are weighted to create this one. We call it activation in this literature. Activation, which is simply linear combination. We've seen that, right? And here is a G function. So you put this one, right? So same number, different weight, different number, different value. So we call it activation function. And this part is what we call as a neuron. And because we are looking at J of them, right? There are J neurons, depending upon which combination, right? There are J combination, so we have J neuron, okay? Then that is converted to another function. So this could be just identity function. So you input this new and get just new. Then that's identity function, right? And this is what you observed. That's observed. So story goes like this. Suppose you observe particular savings bank is failed, bankrupt. Particular savings bank is normal. So suppose there are, let's say, 90 savings bank or 100 savings bank with value 0, 0, or 1, right? So this is the data. For each bank, we look at their financial ratio, Tier 1 capital ratio, or delinquency ratio, or some other ROA, ROE, those numbers, okay? And those are this data. Okay. So if you have magic number, magic weight, okay, then you create this one, okay, and put it through this activation function, so you get some number, okay, get some number. And this could be the function that convert this number from 0 to 1, 0 to 1. Let's assume that. And suppose you get this number 0.6 for particular bank, 0.6. and one is default. Particular bank may have value 0.6. Suppose the other savings bank with their different financial ratio plugged in, given this number, calculate that value, turned out to be 0.01. Very close to being 0, right? And so you can compare these numbers, right? So given some magic number, omega, sets of omega, you have a data, right? Then you might find these parameters that makes this difference as close as possible. Okay? So suppose you found this weight that does that, then you can use this as a model. So go out and collect financial ratios of particular banks and plug it in. You know this number. You know how to calculate this value. And suppose it turns out to be, let's say, 0.2. Then you might interpret that as the probability of that particular bank going default could be 20%. So this kind of model could be applied to develop a prediction model, prediction of default. Okay? We have companies, manufacturing companies, who failed and who survived for a long period of time and collect their data and try to build a model and find appropriate numbers for some informative input and their parameters, and do this, and then you might be able to develop a prediction model, right? Yeah, that's what I mean by this one. So original data with weights created this value, and we call this as one layer. This is one layer, hidden layer. Okay. So input, you have a layer, right? In layer, you have different neurons, right? And then here is another layer. Okay? That was the initial input, right? And somehow that is transformed. And then this is going to be transformed again here. This is second layer. So one layer, two layer, three layer. We don't know how many. But by introducing more neuron or node, same thing. Introducing how many of them? 3, 5, 10. How many of this? 10, 3, 5. How many of them? One layer or two layer? We don't know. But if you happen to choose the right number, then you can create very smooth function for y. Very smooth function. Okay. So this is output unit. So let's go back to this example. So suppose you have $1 exchange rate, and basically this is AR3, right? AR3. This is one layer, so you have only one part. This one. And you see, those are input, these are weight. There is another combination, another combination, another combination. Right? So in this case, inputs are 3, and there are 4 combinations with this weight, where G function is defined in this way. Right? So obviously we know that if these are not 0, then there is a nonlinearity going on. Right? So this is basically one of the simplest kind of artificial neural network model known as multi-layer perceptron model. In this case, hidden layer is just one. So with this combination, actual data is this one. Actual data. And this purple is a fitted value, right? If you have all those numbers, then you can calculate fitted value, right? Is this. The difference, well, if you are given the same data, and fitted least square only linear model, then probably this purple line might not follow that high, right? It might go this way, right? But there is an additional explanation, right? So fitting data better. So if you have these numbers, what is the forecast? Well, you can generate it, right? If you add time t minus 1, t minus 2 is known, right? These are all known, so you can calculate t plus 1, t plus 2, t plus 3, and those forecasts could be plugged back in. You can generate forecast. Right? So many advocates of this artificial neural network built more complicated model than this one to predict stock return, and employed by those security companies in the United States. Their claim, of course, is that if you just look at linear part of stock return, this number may be very small, right? But they usually claim that, well, if you recognize nonlinear components, then they say explanatory power or predictive power increases. Okay. Well, that's good news. Well, if something is better predicted than other cases, well, that's good situation. But the thing is, where are those magic numbers coming from? Like, how many of these terms, neurons, or how many layers? Right? In fact, someone did some experiment and created purely random sequence, and fit this type of model with sufficient number of lagged values and more of this hidden layer. They have very good fit, even though the data is purely random. Okay. So suppose you have very good fit, you found very good fit, and then you try to generate the forecast, right? Then as time goes by, you can see the mean squared error and see if the performance of your proposed model, right? But what appears to be problematic is, in fact, in that particular experiment, you used white noise as a data. By definition, is not predictable, right? So in our literature, time series literature, it's known as overfitting problem. So the reason is, by introducing more of nodes or more of layers, you can approximate this function arbitrarily closely smooth. So you can almost you can replicate this relationship almost as exact, because introducing this layer is exactly what it does. Arbitrarily closely approximate this function. So you explained any pattern that has actually no pattern, but you can arbitrarily closely follow this one in sample. That's the problem. So when it has to go to this direction out of sample, it wouldn't work, right? It wouldn't work. So that's the problem of overfitting, right? So some people say, well, this has that kind of critical shortcoming, but still many are thrilled by this type of approach. We're basically trying to exploit any kind of nonlinearity present in the model, which is not screened by typical linear statistic like correlations. So that's where we are. Okay. When I come back next time, I spend a little time to explain non-parametric model. This one is also related to finding smooth function for f. Okay. But it has different approach than this one. Yeah, that's all I have to say for today. Any question? Is this 12th week? 12th week. Okay. We have 15 weeks up to this semester, right? Next semester we have a 16 week, but this year we have 15 week. So when I counted the first Thursday, first day of a final week is 12th Thursday next month. So would you prefer taking final exam on this day or Monday next week, following week? Let's do it and ignore, forget. Which one? So how many of you prefer first 17th, right? Or 16th? How many of you prefer 16th, Monday, for final? Raise your hand. 4. How many prefer 12th, Thursday? Raise your hand. And undecided?
Do we have more materials to do if we take exam on 16th?
I wouldn't do that. That's not fair, right? The first few days in this week, we have exam week, review week, right? So we won't be covering any new material on Monday that week. So my plan is to hopefully go through some practice exam, like midterm, So I probably cover last year's final exam on Monday this week, and then give you a final exam on 12th, and let you enjoy your vacation. So 12th, right? Okay, this is set. If you're undecided, but still you have to come, right? So don't forget. Okay, thank you very much.